the MS team? Yes, okay. So yes, we have uploaded the lecture slides with notes that was taken during the class, and also everything that I taught will be recorded and provided online in the YouTube channel. So you can all listen to the lecture note again. Another thing that I asked you to do last time is about the fact that we will go through like a coding session a little bit. So before we move into our lecture today, let us look at this lab. I'm not sure it's like a lab homework, lab 1. Yep, you can go through the GitHub page and it's listed on the top left here. Yep. And here's actually like instruction for every lab. I wasn't sure if I have updated them because some of them are like the old one. Maybe I've done it, I'm not sure. Yeah. And go to the lab 1, which will be your homework. And another thing that I asked you to do was to find a group, right? And for this class, let's make it no more than 5 groups, please. And yes, I assume that all of you've done it. Anyway, in the lab 1, you will find README, which will list the, I don't know, it's like materials that have been provided, and also where will you put in your work. That is, there's going to be a Google document where you can fill in the information and like your answer, your analysis, whatever. In here, there's questions where you have to answer each of them. And of course, with this, you can, in order to fill in the information, you probably have to use the GitHub, the code in the GitHub. And actually, in this assignment, we will go through the topic that we will learn today, which is about the cross-validation technique, which is a technique that we will use to split our data. But before that, let us look at it's like a traditional-ish kind of setting, or maybe like a setting that you normally see. That is what we call a hold out. And I think initially when I said the word hold out, cross-validation, you may, I'm not sure, some of you may know already what it is, but just in general term, it's actually like a setting that people normally use, where they have like a data splitting into training, validation, and testing. And that's it. And it's actually a very general setting. But the thing is, with this example, you will see why that setting can be a problem. And probably I would like you to maybe open this on Google Colab, or maybe you can download everything into your local computer and run it, right? Before you run, please make sure you have installed the package for NumPy, Pandas, and Matplotlib, and sklearn. I think I have provided the list of the requirements. Requirements. Initially, you can install these packages through the requirements.txt if you want to do it on your local computer. If you want to do it on Colab, you may have to add a line. I'm not sure, you may need to add a line to say that, okay, you want to install this package.
I tried Colab and that's not required.
Okay, I'm not sure because I remember all time I have to do it. Maybe there are kernel that you already set up that actually have this package installed. But for some of you who start new, you may need to do the installation again. Okay. Anyway, in here you will see, yes, another thing that you may have to find in the lab folder, that is a data set that is called the House Prices Advanced Regression Techniques. Okay, whatever the name was. I actually downloaded this data set from Kaggle. Yeah. So it's actually the traditional house price data set that actually have these set of features. You can see those names. It's pretty long. And the target of this dataset is to do a regression task. That is, they will use these features, or maybe information, which is bunches of them, to predict the house price. Yes, that's a regression. It's not like a predict in the future timestamp, it's just predict at the current instant with these information. So for example, if you want to buy a house, or maybe to rent a place, it's probably, you know that the price of that will depend on maybe how large your house is going to be, or maybe what are the facilities that will be provided. And for that, the house price could go very high, but it may not be that high if it's not in a big, or maybe the center of city area kind of thing. So with those information, it could help you find the good estimation of what the house price could be. And the reason for me to take this as the first thing that you will see today is because we have talked about the data pipeline. That I said that, okay, first thing first, what you should do is actually look at your data. And after that, you will do data splitting, which I have already provided code for that. After that, you will have to do the noise removal. But in this setting, I will not ask you to do that now. What I will actually ask you to do after this is actually, after the data splitting, is actually to do the feature selection. And actually, the number of features will be your hyperparameter, one of your hyperparameters. And the set of your feature will also be another hyperparameters. And yes, and as you can see, because you have these many features, your hyperparameters will be in a large number. But the thing is, you have large set of features. But it depends now on whether or not you have also a large set of data. Because if you think about if you have a small set of data, but you have large number of features, that means a little change by your feature selection could impact the overall performance. Because your data splitting maybe happen to split on the data that is not reflecting the situation that you choose. But somehow when you change that setting, it will reflect on your data. So that's the reason why I kind of picked this data set specifically, because you will see that the number of training data, or maybe the number of samples in this setting, is actually not that high. And it will be the particular setting, and actually you can see in future, if you have this kind of setting, you have small amount of data, but you have so many hyperparameters to find, you have so many parameters to set, and the problem will be when you run each and every time, you will get different result. And because of that, hold out method will not work well in this case. You will need something called cross-validation. But you will learn in future as well that cross-validation or k-fold cross-validation is actually a technique that we don't really use in practice, especially if you have maybe I would say, maybe 10,000 of data. You will start to feel like you don't want to use it because it actually takes lots of computational efforts. But in this particular data set, when your data set is around thousands, you will see clearly that when you change your setting, your performance will change. And in fact, even if you choose the same setting, but your randomness is different, then you get different result. And that is when hold out, the generic data splitting will not work. Okay, this is the set of features. And yes, around this process, you may see that in some features, you may have missing data. And for that, in this example, I actually choose those features that most likely to be the feature that reflect the house price, and they are the set of features that have the least missing information. So it's appropriate, yeah. And then After you have this set of features, you may want to do some kind of transformation. In this case, I do some label encoder, and that is because some of these features may not come as a scalar value, but it's more like a label. And it's actually a good practice for you to turn those labels into one-hot encoding. And with that, you could do the label encoder as in the transformation to help with the transforming these set of features into label. These set of features that has label into the, let's say, like a one-hot encoding. After that, we will then do what we call data splitting. And before that, I actually dropped the NAND, And after data splitting, we will do some transformation. This transformation is, I think, if I remember correctly, is the same as the, not sure what kind of transform that is, but maybe it's just data scaling. You can look at them. In regression method, not only you should transform your label into one-hot encoding, you should also consider scaling the range of values. Yes, in regression, but when it's come to deep learning, you don't normally need to do that. Because if you imagine data scaling could also reduce some information. And for the data-driven methods or data-driven approach, the non-parametrics one, they will work better if you don't scale your data. Also, tree-based method will work better if you don't scale your data. So there are exceptions and there are rules that you have to remember. But anyway, this is going to be the correlation plot between your target house price versus the rest of the, like the features. Yeah, the features that I chose. So in this case, you may see that there are some features that strongly correlated with your target value. And there are some that aren't that correlated. And actually, these correlations are taking the value from -1 to 1. So in fact, those features that has value like a negative, nearly -1, is actually have some kind of correlation that is a negative correlation. In fact, this plot may be better if I were to use something like an absolute value instead of allowing it to go between 0 and 1, because the data mapping may show me something that is not, let's say maybe, it's kind of like how would you reflect this correlation. Negative correlation is correlation. It actually could be high correlation, but it's just opposite direction. That could be used as well. So that's what I'm trying to say. After that, after feature selection and all that, here we apply linear regression. And as you can see, when we train that machine learning, I use only the training. So that is when I said that we use the training data to get model parameters. It's actually the model parameters in your machine learning. But your hyperparameters will go where you want to then choose which set of your hyperparameter settings is the best. So once I train my machine learning, right, I get some performance. I can see that, okay, this is how it works. I maybe do something like, okay, do evaluation and see this is the performance on the testing performance. But then what I also noted is that with that set of the data that I choose, it may not be the best. Or maybe the set of features that I chose previously may not be that optimized. So then I start to sorting each of these feature settings. And this is where I will use not just training and testing, but training, validation, and testing. So the training itself will use just the regression. But after that, after the training, then I will have to use the validation. Okay, the valid data. Okay, actually, my validation is run around here. You can see after I train, I run inference on my training. I have the Y train predict. That's why train predict is actually the prediction result given the training. And then I do the validation, inference on the validation. That is to get the result from my validation data set. And the reason that I have to do both training and valid, in fact, if this were my actual setting, I can skip on the training if I believe that the model fitting or the training of that machine learning works perfectly. But I still recommend showing the inference on the training, that is to cross-check whether or not your training is working as expected. How will you know if your training worked as expected? If your training performance is getting better and better when you feed more data. It will get better no matter how bad that performance on the validation or testing may be, but on the training it will always get better because you are training or optimize your model using the training data set. And that's why we need validation data set. The validation will only use in doing the inference, but in fact it's used to calculate some scoring. Okay, you can see RSS, TSS, RSE are all the scoring that we've learned last week. I also calculate the RMSE, and after that, yes, BCE, AIC scores are going to be what we learned today. And in fact, the AIC, BAC, and adjust R-squared scores will actually be those scores that you use with just the training. You don't need to use it with the validation. Okay, there are some scores that will need you to use validation and some scores that will be need to calculate with the training, or maybe you can do just fine with the training. Anyway, after that, you can plot your validation and training, RMSE. And as you can see, in fact, this graph is showing me that I can actually increase more number of features. Or maybe I can further go with the settings that I chose, like setting number 10, and maybe add one more in setting number 11, and to see when that, RMSE may spike up. But the thing is, this is like I run only, one selection of training and validation. I didn't do multiple subsampling of them. In general, we usually do this if we have large amount of data. But if you imagine you have maybe 100,000 amount of data, if you keep subsampling them, it could take a long time. But this is like just one time. But in the case that your data is very small, doing this one time, you may have different results each one. So you can try that Google Colab right now and run this plot and see if you get consistent result. I think you wouldn't get consistent result given the fact that your training data is actually quite small. And this is another plotting that involves another scoring mechanism. The AIC, BIC, and adjust R-squares, those will not be consistent. And actually, the computation of those scoring is recommended to use with training. So yes, sorry that I kind of include something that I never lectured before, but this is just like an example of what like a whole pipeline might look like if you do if you do the hold out technique. And in fact, your homework is not to do hold out, because I gave information about hold out. Your homework is to do the k-fold cross-validation, which is what we're going to lecture today. But this to give you an idea of what a hold out is. And I think once you've seen this hold out technique, you will see that it's actually the common things that we've done. We split our data and just run it, right? And maybe just vary the hyperparameter setting, and that's it. But the thing is, there are other techniques, especially when your hold out performance is being inconsistent. When I say inconsistent, you should just do the Colab and run. You will see that the graph that I said, this one, actually the last two plots that I said, that I mentioned before, these two plots, this one And this one will change each run. Actually, this one I choose a good one. But in each run, you may get different, rather drastically different result. And the reason that it's different is because there are some random initialization that happen around data sampling. That is when I try to split the data, which is here, the algorithm here that I use to split. You can see I use NumPy random. That is when I randomly select the data, and each selection, especially if my dataset is small, you will get different samples for training, validation, and testing. And that's the reason why if you run everything just one time, you will get different result from previous time because it happened to sub-samples your data differently. But if you have large amount of data, this sampling will not have a lot of effect. And that's why these days when people talk about deep learning, they will automatically do the hold out because it's simpler and they usually comes with large amount of data set. Okay. All right. Do you want to play with the code? Or you want me to do the lecture?
Anything.
Anyone want to look at the code first? Okay, let's pause a little bit and see how you go with this, and I will then go with the lecture.